We shall now go through the salient feature and the important and crucial part of matrices, that is determinants. Corresponding to every square matrix A, we assign a fixed number called its determinant. So that fixed number, it will be according to the nature of the elements of the matrix. Therefore, corresponding to every square matrix A, we assign a fixed number called its determinant, denoted by that A as follows. So determinant will be existing for every square matrix only. We speak of the determinant of a square matrix only. How can we define? Okay, let us consider a square matrix. Least possible order of a square matrix, one by one. From that stage we start. Look here. If A is equal to a 1 by 1 matrix like this, then we define that A is equal to the element present in that. Therefore, if A is equal to only 1, then that A is 1. If A is equal to 15, 1 by 1, that A is equal to 15. So there is no question of any separate procedure to find the determinant of a matrix of this form. We just have the entry or the element present in that. That gives you the determinant. This is the first case. Okay, second case. What is the second case? 1 by 1 order we have discussed. Now let us look at 2 by 2 square matrix. A, B, C, D, like that. In this case, we define that A or the determinant of A as the difference of the cross products AD minus BC. As you know, it is difference of the cross products AD minus BC. Let us now observe some determinants, 2 by 2 determinants. Moreover, we habituate to write, if you write like this, it is a matrix. If you write like this, it is the determinant of the matrix. What is that? AD 7, BC 30. 7 minus 30 is minus 23. Okay, one more. 4, 1, 2, 7. Come on, what is the determinant? 28 minus 2 is 26. One more. 1, 5, 2, 10. Come on, this is 10 minus 10, 0. Observe these three answers. One answer is positive, one answer is negative, and another answer is 0. So, in whatever fashion it may be present, whatever fashion we observe the nature of the value of the determinant. Sometimes it is positive, sometimes it is negative, sometimes it might be 0. Okay. Next one. Consider these determinants. Determinant 1, 4, 2, 8. What is the value of the determinant? It is 0. It is 0. Just like that, you consider the determinant 4, 5, 6, 2. Come on, what is it? 8 minus 30, it is minus 22. This is 0, but this is not 0. Hereafter, we shall call those square matrices whose determinant is 0 is singular, and that which is not 0 is non-singular. Therefore, from this view, the matrix 1, 4, 2, 8 is singular. And the matrix 4, 5, 6, 2 is non-singular. What do you mean by a singular matrix and what does it mean by a non-singular matrix? Suppose A is a square matrix. If det A is equal to 0, then it is singular. If det A is non-zero, then it is non-singular. Now, so far we have seen the determinants of 1 by 1 matrices and 2 by 2 matrices. What about 3 by 3, 4 by 4, 5 by 5, like that? In general square matrices, how do you define the determinant? And for that, we need two more new concepts, namely minors and cofactors. Yes. Minors and cofactors of elements of a square matrix. Observe the heading. One thing is sure, we are going to learn the two words minors and cofactors of elements of a square matrix. How to define them, how to calculate them. Let us now study. Let A is equal to 1, 3, minus 1, 4, 2, 7, 5, 6, 9. First of all, let us know the minor. What do you mean by a minor? The definition is like this. If Aij is an element of a square matrix A, then the minor of Aij is denoted by Mij and is defined as Mij is equal to the determinant obtained by deleting ith row and jth column from A. The sentence may look somewhat a lengthy sentence, but the way in which we follow this meaning is very simple. If A is an element of a square matrix A, then the minor of A is denoted by Mij and is defined as Mij is equal to the determinant obtained by deleting its row, ith row and jth column. That is, the row in which it is present and the column in which it is present. This is the meaning of the word minor of Aij. Okay, let us calculate the minors so that it will be understood very clearly. Well, my dear, what is M11? What do you mean by 1? Minor of the element present in first row and first column. First row, first column, you delete them. What is going to be remained? 2, 7, 6, 9. What is the determinant? 18 minus 42. 18 minus 42 is equal to minus 24. And I like to have M12. What is that? M12. Minor of element present in first row, second column. Delete first row, delete second column. What remains here? 4, 7, 5, 9. Isn't it? It is 36 minus 35. So it is 1. And at random, I like to have some M23. What is the meaning of that? Second row, third column. Minor of the element present in second row, third column. So you delete second row and you delete third column. What will be remain? 1, 3, 5, 6. So that it is 6 minus 15. So this minor is minus 9. And let us have one more minor. Say, I like to have M31. What is meant by that? Minor of the element present in third row, first column. Third row, first column. You delete them. What happens? 3 minus 1, 2, 7. Isn't it? So what is the answer? 21 minus 2 is nothing but 23. Like that, we define the minor of an element of a square matrix. Okay, these are minors. How many minors will be there for A? As there are 9 elements, 9 minors will be there. If A is a 4 by 4 matrix, how many minors of the elements will be there? 16 elements are there, so 16 minors will be there. Well done. Next one. Cofactors. What do you mean by cofactor? Now this is our turn to look at the meaning of the word cofactor. The cofactor of an element Aij in a square matrix A is denoted by Cij and is defined as Cij is equal to minus 1 whole power I plus j into Mij. Please understand the definition carefully. Minus 1 whole power I plus j. What do you mean by I? The row in which the element is present. J, the column in which the element is present. The element for which we are ready to have the cofactor. That element is nothing but minus 1 whole power I plus j into Mij. What is Mij? Previously we have noted it. What is Mij? Minor of the element Aij. This is the definition of cofactor, and it will be quite convenient for us to have the cofactors of all the elements in A. What happens? First of all, C11. Let me calculate. What is the meaning of this C11? Cofactor of the element present in first row, first column. We should start with minus 1 whole power 1 plus 1, and then minor. Delete first row and first column. What happens? 2, 7, 6, 9. Minus 1 whole power 1 plus 1 is 2. Minus 1 whole square is 1. So the no change in sign. 18 minus 42 is equal to minus 24. Just like that, C12 minus 1 whole power 1 plus 2 into minus 1 whole power I plus j. 1 plus 2 into first row, second column. Delete them. 4, 7, 5, 9. What is it? 1 plus 2 is 3. Minus 1 whole cube is minus of, come on, 36 minus 35. What is it? Minus 1. Actually it is 1 minus 1. And C13, suppose you have minus 1 whole power 1 plus 3. First row, third column. Remove that. 4, 2, 5, 6. 1 plus 3 is 4. Minus 1 whole power 4 is positive. So 24 minus 10 is nothing but 14. Likewise, you can have C23, C31, like there is an example. Let me find C23. What is this? Minus 1 whole power 2 plus 3. Second row, third column. 1, 3, 5, 6. What is the determinant? 2 plus 3 is 5. Minus 1 whole power 5 is minus of 6 minus 15. 6 minus 15 is minus 9. Minus of minus 9 is 9. That is the cofactor of the element which lies in the place second row, third column. This is the way we find the cofactors. Well, there has been a beautiful property of cofactors. You can look here. What are these cofactors? 1 1th place, 1 2th place, 1 3rd place. You can recollect these are all the elements in the first row. We can call these cofactors of elements of first row. Cofactors of elements of first row. Now, look at this. You multiply first next element into its cofactor minus 24, next element into its cofactor minus 1, next element its cofactor 14. Altogether how much? Minus 24 minus 3 minus 14. Isn't it? Minus 24 minus 14 is minus 38, minus 3 is minus 41. What you could have done is, we have found sum of the products of the elements of first row with their corresponding cofactors. Well, my dear, you do the same work in view of second element, second row. What will it be? Let us observe. 4 into, what about its cofactor? Cofactor is just nothing but minor, but of course minus 1 whole power I plus j. Second row, first column, isn't it? Second row, first column. 2 plus 1 is 3. Minus 1 whole cube is minus of. So minus of, batao, please tell me. Delete the second row, first column. 3 minus 1, 6, 9. 27 plus 6, 33. Isn't it? 27 plus 6, 33. Next, 2 into cofactor. Second row, second column. Minus 1 whole power 2 plus 2 is 4. Isn't it? You see, you can have a fixed understanding in your mind according to the place values or the places. You can assign the sign to be given before the cofactor. First row, first column, 1 plus 1, 2, plus 1 plus 2, 3, minus 1 whole cube is minus 1 plus 3, first to third column, 4, plus, minus, plus, minus, plus, minus, plus, minus. Anywhere you proceed, alternate plus and minus, plus, 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 like that. You do not use that in a diagonal way, plus, plus, plus. Yes, don't proceed in that way. So plus, minus, plus, minus, plus, minus, etc. Okay, right, plus 2 into second row, second column. We deleted 9 plus 5, 14. Plus 7 into minus, plus, minus, isn't it? Minus, come on. You delete second row, third column. 6 minus 15 minus 9. 4 into 33 is 4 30s are 120 plus 12 is 132 plus 28 plus 63. Like that you can proceed. Take a particular row as you like. First row, elements of first row, multiply these elements with the corresponding cofactors and have the sum. Again you do the business for second row. The sum of products of elements of second row with their corresponding cofactors. Similarly, sum of the products of the elements of third row with the corresponding cofactors. Again you have the same number, and that is of course the heroine of the topic. This is the determinant of A. Previously we have defined the determinant of a 1 by 1 matrix and a 2 by 2 matrix. From 3 by 3 and thereon, determinant of a square matrix is now defined as sum of the products of the elements of any row with their corresponding cofactors. That is the determinant. You see, another beautiful property of these cofactors is sum of the elements of, sum of the products of the elements of any column with their corresponding cofactors is again the same value, the determinant. Isn't it? Okay. Suppose capital A is equal to A1, B1, C1, A2, B2, C2, A3, B3, C3. Let me represent the cofactors of these corresponding letters with their corresponding capital letters. Then that A is equal to A1 plus B1 plus C1 is equal to A2 plus B2 plus C2 is equal to A3 plus B3 plus C3. What is this? Some of the products of the elements of first row and their cofactors, second row and their cofactors, third row and their cofactors. You see, it can be done in view of columns also, like this. What are you? A1 plus A2 plus A3 B1 plus B2 plus B3 C1 plus C2 plus C3. In any way you can proceed. Another beautiful character of the cofactors is, look here, what are A1, B1, C1? Elements of first row. What are A2, B2, C2? Cofactors of the elements of second row. If you have the sum of these products, you will have 0. Yes, if you multiply the elements with the cofactors of these elements only, you will have that A. Elements are these, cofactors are of these elements. Then A1 capital A2, B1 capital B2, C1 capital C2, 0. Similarly, A1 capital A3, B1 capital B3, C1 capital C3, 0. Similarly, column wise also, A1 capital B1 plus A2 capital B2 plus A3 capital B3, 0. A1 capital C1 plus A2 capital C2 plus A3 capital C3, 0. Similarly, B1 capital C1 plus B2 capital, like that. So you can prepare these two sentences. Sum of the products of elements of one row, in brackets, column, with their corresponding cofactors is always constant, called the determinant of the matrix. Similarly, the sum of the products of elements of a row with the cofactors of corresponding elements of second row or another row, then it is 0. Corresponding elements, corresponding in that sense, suppose we are considering these two rows. Element is here. What is the corresponding element in the next row? This is A1 capital A2, B1 capital B2. Like that you have to find the product. It's not like that A1, B2. No, you should not like that. A1, A2, B1, B2, like that. If you do so, it becomes 0. It becomes 0. Well done. Let us now prepare those two sentences carefully. If A is a square matrix, then first sentence, the sum of the products of elements of any row with their corresponding cofactors is always constant, called the determinant of A. Determinant of A. But you see, if you take the elements of first row and cofactors of the elements of second row and find the sum of the product, then it becomes 0. the sum of the second sentence, the sum of the products of elements of any row or column with the cofactors of corresponding elements of another row or column is always 0. Always 0. These two are the beautiful properties of cofactors. Yes. And by noting down this definition, we shall now try to find the determinants of some famous matrices. Consider the matrix or determinant 1, minus 1, 1, 2, 3, 0, 1, 4, 5. What is the determinant? Just now we have noted, you need not find all the minors or cofactors. It is just enough to have the cofactors of one particular row. Let me consider the first row. 1 into its cofactor. First row, first place, so positive. Minus 1 whole power 1 plus 1. You delete the first row and first column. 3, 0, 4, 5. What is this determinant? 15 minus 0 is 15. Minus. Why should you put minus here? We have moved to the second place. First row, second column. According to the cofactors rule, minus 1 whole power 1 plus 2. 1 plus 2 is 3. Minus 1 whole cube is minus of. That is why I have put minus. Into its cofactor. Delete the first row and second column. 2, 0, 1, 5. 10 minus 0 is 10. 10 minus 0 is 10. And then the third element, plus 1 into. You have moved with plus sign. Why? Because first row, third column. 1 plus 3. Minus 1 whole power 4 is plus. Into. You delete the first row and third column. 8 minus 3, it is 5. It is 5. So it is 15 plus 10 plus 5 is 30. So its determinant is 30. As an example, we have done that. One more thing. 1, 2, 3. 2, 3, 4. 3, 4, 5. What is the determinant? This is A. That A is equal to, come on, tell me. 1 into 15 minus 16. Minus 1. Minus 2 into 10 minus 12. Minus 2. Plus 3 into 8 minus 9. Minus 1. This is minus 1 plus 4 minus 3. What is it becoming? It is 0. Later on we shall discuss among the properties of determinants. You observe here, these are an AP, these are an AP, these are an AP. In such a case, you need not calculate the determinant. It will be 0. Not only this, you observe this. A is equal to 1, 3, 5. 4, 7, 10. 6, 11, 16. You observe the elements. These are an AP. Difference is 2. These are an AP. Difference is 3. These are also in AP. Difference is 5. Here also, if you want, you can calculate. You calculate it. That it definitely becomes 0. You calculate. What is the reason? All the 3 rows are in AP. Are in AP. You see, 1, 4, 6. These are not in AP. It's not enough for us. It is not needed for us. We have seen that the 3 rows are in AP. Then the determinant is 0. Yes. Next. Properties of the determinants. The next heading is properties of determinants. Very first property. Suppose one of the rows contains all zeros, then the determinant is 0. Or one of the columns is filled with zeros, then also the determinant is 0. And if you want to prepare the sentence, they will be lengthy, it's not enough. You look at that and understand. Okay, then next one. If any two rows of a determinant are equal, then also the determinant is 0. Here the first row and second row have equal elements. You see, it need not happen in the case of rows only. It may happen in the case of columns also. Look here. This is equal to A, B, C, P, Q, R. P, Q, R. This is also 0. One more thing. A, B, C, K, A, K, B, K, C, D, E, F. What do you understand this? The elements of first row and second row are proportional. That is, this element by this element is 1 by k. This by this, this by this, this by this. The ratios are equal. It does mean that they are proportional. If they are proportional, then also the determinant is 0. This is equal to A, B, C, D, E, F, K, D, K, E, K, F. Here, elements of second column and third column are proportional. Even then, the determinant is 0. Even then, the determinant is 0. Well, these are the basic properties of determinant. There are so many other properties, and making use of these properties, I like to ask you one simple question. You try to tell me. Look here. 1, 3, 5, 4, 5, 9, 8, 10, 18. What do you say about this? What do you say about this? What is the determinant? Observe the elements of second row and third row. Elements of third row are just 2 times those of second row. Should you calculate it? No, it is surely 0. It is surely 0. One more thing. 1, 5, 7, 2A, 2B, 2C, 3A, 3B, 3C. What do you say about this determinant? What is 2A by 3A? 2 by 3. 2B by 3B? 2 by 3. 2C by 3C? 2 by 3. The ratios are equal. What does it mean? They are proportional. If they are proportional, then also the determinant is 0. Then also the determinant is 0. Yes. These are the beautiful properties, the basic properties. Next, let us turn towards the remaining properties of determinants. Next, property number 4. Look here. A, B, C, P, Q, R, X, Y, Z. Suppose a particular determinant is there, and for some purpose I need to interchange these 2 rows, say the second row and third row. What is going to happen? A, B, C, X, Y, Z, P, Q, R. What you mean to say is, the next property says that if any 2 rows or any 2 columns are interchanged, then the value of the determinant gets the opposite sign. Value of the determinant gets the opposite sign. Yes. And here, suppose I have interchanged first column and second column. What happens? B, Q, Y, A, P, X, C, R, Z. Then also, that is, this property says that if the elements of any 2 rows or any 2 columns in a determinant are interchanged, then value of the determinant gets the opposite sign. Value of the determinant gets the opposite sign. Yes, this is this property. Next one. Look here. Suppose we have ABC, PQR, XYZ. a particular determinant is there. And if you could observe the elements, you have noticed that a particular number is a common factor for all the elements of a particular row. So say first row. First row is say Ka, Kb, Kc. Then you can pull that K out from one row itself. A, B, C, P, Q, R, X, Y, Z. This can be expressed in another way also. If the elements of a particular row are multiplied by K, then the entire determinant gets multiplied by K. One more thing, this is suppose LA, LB, LC, MP, MQ, MR, NX, NY, and Z. What is the fate of this determinant? You can get L out from the first row, M from second row, N from third row. So that this is A, B, C, P, Q, R, X, Y, Z. You can get as a common factor. Okay, this is the property. So in a sentence, what can you explain? How many, in what way you can explain? If the elements of a particular row or column in a determinant are multiplied with a constant K, then the determinant also, value of the determinant also gets multiplied by K. K times the determinant you will have. Well, next, look here. A is equal to A, B, C, P, Q, R, X, Y, Z. What is 2A? 2A, 2B, 2C, 2P, 2Q, 2R, 2X, 2Y, 2Z. What is det 2A? Determinant of this. You can get 2 from first row, from second row, from third row. Altogether, 2 cube into A, B, C, P, Q, R, X, Y, Z is nothing but det A, isn't it? 2A means every element of A is going to be multiplied with 2. So in every row you can have a common factor 2 out. 2 from first row, 2 from second row, 2 from third row. And in general, suppose A is an n by n matrix, then what is that Ka? Imagine. Ka means every element of A is going to be multiplied with K. So we have K from first row, K from second row, K from third row, like that. How many rows are there? It has been given that A is an n by n matrix. Therefore, det Ka is equal to K power n into det A. K power n into det A. So these all come under one particular property only. What is that property? If the elements of a row or a column of a determinant are multiplied with a scalar K, then value of the determinant also gets multiplied by K. Yes, of course. With that simple property, we could have designed this also. Det Ka, what is det Ka? K power n into det A. Okay, right. I'd like to ask you one simple question. If A is equal to 1, 5, 6, 7, 8, minus 1, minus 2, 0, 5, then det 2A is equal to, first option, 4 into det A, second option, 6 into det A, third option, 10 into det A, fourth option, none. What is the right option? How many rows are there? 3 rows are there. What is asked here? Det 2A. 2A means 2 can be pulled out from first row, second row, third row. So 2 into 2 into 2, 8 times it becomes. So 8 into det A must be the answer, and it is not available. So in this case, what is the suitable option? None. It is none. Another beautiful property. If there is a determinant, say A, B, C, P, Q, R, X, Y, Z, then if you interchange 2 rows, the value of the determinant gets the opposite sign. 2 columns, same. Now I like to interchange all the rows and columns. What happens? This is A, B, C, P, Q, R, X, Y, Z. In this case, the determinant does not change. What I mean to say is that A is equal to that A transpose. That A is equal to that A transpose. If the so-called interchanging is done with respect to just 2 rows only, then value of the determinant gets the opposite sign. Whereas if you are able to interchange all the rows and columns, that is, if you can find the transpose, then that A is equal to that A transpose. That A is equal to that A transpose. Yes. Next one, you consider this example. 1, 2, 1, 4, 2, 1, 4, 5, 6, 1, 2, 8, 0, 1, 3, 4. What do you say about this? This is a 4 by 4 determinant. Suppose in a particular case, you may need to shift this first column to this, translating. So what I mean to say is, this becomes the fourth column. First column, second column, third column, fourth column. Like that. Come on. Then, what do you need if you like to transfer this to the fourth place? All of them will be translated. Second column becomes the first column, third column becomes the second column, fourth column becomes the third column, and the first column becomes the fourth column. Then this is equal to how many columns you have translated? 3 columns minus 1 whole cube into 2, 1, 1, 1, 1, 4, 2, 3, 4, 5, 8, 4, 1, 2, 6, 0. You have transformed this to the fourth place. So this, you would like to see this as a fourth column. This is the first column, second column, third. In a similar way, suppose you would like to consider this to the fourth column. How many columns you have trespassed? 2 columns. In that case, it is minus 1 whole square into 1, 2, 6, 0. 1, 4, 2, 3, 4, 5, 8, 4, 2, 1, 1, 1. Minus 1 whole square means no changes at all. This cannot be expressed in a small sentence. Some big sentence will be observed here. So you just keep in your mind. In a big, what I mean to say is 4 by 4 or 5 by 5, some things are there. If you transform or transfer one particular column, trespassing some I rows or I columns, then minus 1 whole power I times the determinant changes. Like this. Okay. Next one. There are some more properties. To understand those properties, we need to learn a particular word, namely elementary operations. Elementary operations. There are 3 types. First one, actually speaking, what do you mean by operations? If a matrix is given according to one purpose or necessity, we may be transforming the rows, columns, multiplying a row with a particular constant, interchanging of rows, or multiplying a particular row with some constant k and adding those results to those of another row, like that. All these types of steps, or rather actions, are put in an order called elementary operations. These elementary operations are of 2 types: elementary row operations, elementary column operations, isn't it? So they can be split into 2 ways. What are they? Row operations, column operations. These are of three types. Number one, this symbol, if at all you perform the operation of interchanging the ithro and jthro in a matrix or a determinant, that transaction, that change is expressed by this symbol. Interchange of ithro and jthro. Absolutely in the similar fashion, the corresponding column operation is interchange of ithro and jth column. The second one is, you observe this, elements of ithro are multiplied with the constant k. What is the corresponding column operation? Elements of ith column are multiplied with the corresponding with the constant k. The third one, Ri is changed. Ri in the sense ithro is changed. How does it change? To the elements of ithro, k times the elements of jthro are being added, isn't it? Jthro remains as it is. What is the row going to be changed here? Ithro. In what way are you able to, or are you liking to change it? To the elements of ithro, k times the elements of jthro are being added. What is the corresponding column operation? To the elements of ith column, k times the elements of jth column are being added. Well, my dear, let us understand the effect of these operations in view of determinant. In a particular determinant, if ithro and jthro are interchanged, the determinant will get opposite sign. If a particular row or column, the elements of a particular row or column are multiplied with a constant k, then if the original determinant is delta, then by applying this operation, the delta will be changed with the sign. And if ithro, the elements of ithro are multiplied with a constant k, the resultant determinant will be k into delta, k times. The most safest, the most convenient, the most useful, flexible, beautiful property is this. Even if you apply this, value of the determinant does not change. It remains as it is. Let det A is equal to delta. Let A be a square matrix and determinant of A is equal to delta. If you perform this operation, what happens to the determinant? Minus delta. If you apply this operation, what happens to the determinant? K times delta. And if you apply this operation, there will be no change to the value of the determinant. It remains unchanged. This is the next property we would like to learn. The most useful result is this. And in similar fashion, if you apply this one, the determinant will be get minus sign. If you apply this one, the determinant will be k times the original determinant. And if you perform this operation, there will be no change to the determinant. So, these three operations and those three operations together called elementary operations. And among these elementary operations, the safest operation is if the elements of k times the elements of a row are added to those of another row, then the value of the determinant remains unchanged. This is the property. This is the property. And you can express this in terms of a small sentence also. What is that sentence? If k times the elements of jthro are added to those of ithro, then value of the determinant does not change or remains unaltered. In a similar way, if k times the elements of jth column are added to those of ith column, then also value of the determinant does not change. Yes, This is the benefit of elementary operations. Please have a note of that. Next, and one more property. You observe this determinant. A1 plus A2, B1 plus B2, C1 plus C2, X1, X2, X3, Y1, Y2, Y2. What is the speciality in this determinant? The elements of first column are they appear as the sum of two different elements. Such a determinant can be split as two determinants, the sum of two determinants with the first set A1, B1, C1, X1, X2, X3, Y1, Y2, Y3 and A2, B2, C2, X1, X2, X3, Y1, Y2, Y3. Like this we can split. Okay, if such thing happens in a first row or second row, then also you can split. And in most of the cases we shall be coming across such determinants. It can be split into like this, isn't it? Okay, this is the next property of determinants. You consider the matrix. Observe the matrix on the board. No doubt it is 4 by 4, of course, square matrix. We are to find its determinant, that A. My dear friend, I think you could have noticed and recollected the nature of this matrix. Could you trace it? It is just upper triangular matrix, isn't it? It is upper triangular matrix. Upper triangular matrix. In the case of an upper triangular matrix, it is just enough to find the product of diagonal elements 1 into 2, 2, 21, 2, 25, 10. That's all the determinant. Okay, what is the reason for that? Let us proceed systematically according to the concept. 1 into its cofactor. Come on, what do you mean by cofactor? You delete this row and this column. What happens? This part becomes 0 into 0 into 0 into 0 into. You need not have. So this determinant is this minor, that is this determinant. Again, this is 2 into this determinant. This is 1 into 5. So that is the conceptual reason behind that. Therefore, if at all there is an upper triangular matrix, the value of the determinant is just the product of diagonal elements. Product of diagonal elements. Just like that, suppose A is equal to, you observe this 1, 0, 0, 0, 0. 2, 1, 0, 0, 0. 3, 0, 5, 0, 0. 1, 2, 3, 4, 0. 0, minus 2, minus 5, 7, 1. Observe this matrix. This is the 5 by 5 square matrix. And the speciality in this is a lower triangular matrix, isn't it? It is a lower triangular matrix. My dear friend, whether it is upper triangular or lower triangular, it is just immaterial. If you want to have its determinant, you just find the product of diagonal elements. What is the product of diagonal elements here? 20. So that A is equal to 20. That A is equal to 20. Observing these two examples, what can you state about the property of determinants regarding triangular matrices? If A is a square matrix which is also triangular, then the determinant of such a triangular matrix is product of diagonal elements. Product of diagonal elements. That is a beautiful character which helps us a lot in so many other examples also. Yes, it helps us. Let us now observe in what way it does help us. In what way it helps us, we shall be going to see. Okay, I think you have noticed, if at all there is a triangular matrix, either upper triangular or lower triangular, it is immaterial. If at all it is triangular, then its determinant is of course the product of the diagonal elements. Well done. Let us consider one more example. Look here. 1, 3, 5, minus 1. 0, 0, 2, 3. 0, 0, 5, minus 17. 0, 0, 0, 123. What is the determinant? This is a 4 by 4 matrix. What is its determinant? You see, that is surely upper triangular. The luckiest thing here we have is, this is the diagonal, and those are the diagonal elements. And if you want to have the determinant, it is just the product of the diagonal elements. And one of the diagonal elements is 0. Hence, here det A is equal to 0. Within a second, we will be able to have the answer. Why? Because one of the diagonal elements is 0 and also it is a triangular matrix. As we are given to understand that the determinant of a triangular matrix is just nothing but the product of diagonal elements, its determinant is 0. Its determinant is 0. Okay, we have seen so many cases of triangular matrices. It is upper triangular, it is lower triangular, and this is upper triangular. Here all the diagonal elements are non-zero. Here all the diagonal elements are non-zero. Here one of the diagonal elements is 0, hence its determinant is 0, and these two determinants are non-zero. That is, these two matrices are non-singular. I think you could have remembered it. If there is a square matrix whose determinant is non-zero, then we call it a non-singular matrix. This is a non-singular matrix. This is a non-singular matrix. This is a non-singular matrix. Okay, then I would like to give one particular sentence. You follow the sentence carefully and you tell me whether it is true or not. Every strictly triangular matrix, every strictly triangular square matrix is singular. What do you say about it? Could you remember what is meant by strictly triangular matrix? It is either upper triangular or lower triangular. All the diagonal elements are also zeros. In such a case, we say that is a strictly triangular matrix. Come on, my dear. Let me give you the example of a strictly triangular matrix. Look here. 0, 1, 5, 6, 7. 0, 0, 1, 7, minus 1. 0, 0, 0, 9, 10. 0, 0, 0, 0, 0, 2. 0, 0, 0, 0, 0. This is a 5 by 5 matrix. Look here. Strictly triangular. First of all, it is triangular. So its determinant is 0. Its determinant is 0. Good.